Hello everyone. In today's lecture, we are going to build on the previous lecture and we are going to discuss about the control problems in the temporal difference methods. Remember that the prediction problem is where, given a policy, we are trying to determine the value function for the policy. And this we saw in the previous lecture about how temporal difference methods is used to write down an update rule. So the update rule is written as follows: v of s plus alpha times. Now here you have rt plus 1 plus gamma times v of s dash minus v of s, where v of s dash is the next step. And this update rule is used to update the values of all the states. And this is exactly how the prediction problem is solved for using the temporal difference methods. We also looked at how TD methods offer a significant advantage compared to Monte Carlo methods, especially that you don't need to wait till the end of the episode for making an update. And they are quite similar to dynamic programming in some ways because there is an element of bootstrapping which is involved in the temporal difference methods. When we bootstrap, we use the values of the next states to update our values of the previous states. And this is exactly what we do in both dynamic programming and Monte Carlo methods and temporal difference methods, but we don't do this in the Monte Carlo methods, where we use the entire return of the episode. Now, what we are going to do is that we are going to understand how to solve the control problem. And remember that in the control problem, what we are trying to do is that we want to find out which policy is the optimal policy. So now that we have understood how to estimate the value function for a given policy using temporal difference methods, can we nudge the policy towards the optimal policy? And we looked at in dynamic programming as well as in Monte Carlo methods. Usually, this process uh, is recursive. In other words, you update the policy, then you again change the value function, then you again update the policy, and this back and forth methods or this back and forth algorithms continue until you get uh, a converged optimal policy and the value function for that optimal policy. In the Monte Carlo methods, we looked at how exploration and exploitation can be used in the control problem. Uh, we saw that instead of parallelly computing the value function and uh, the policy, we calculate the action value function instead of the state value function. And there we understood how an epsilon greedy policy worked the best. So let's do a quick recap of that so that it will build some foundation for us to discuss this. Uh, in the Monte Carlo method, what happens is that the agent follows a specific number of states till the end of the episode, and then you update the value function of the states based on this entire episode, based on the return from the entire episode. Now, when you are trying to optimize for the policy, from this state S, let's say there are three possible actions: A1, A2, and A3. And if, let's say, A3 is the action which is giving you the maximum returns, but your agent has only explored A1, then it's not going to help you because the agent has not explored A2 and A3 at all. This problem did not happen in dynamic programming because all the actions were explored because we knew the model of the environment. So that is why we have to do a process which is called as exploration. And exploration means that even if your uh, even if your action value function, which is q of s comma a, even if this action value function is telling you that action a1 is maximum, action a1 is having the maximum value, So if even if let's say q of s comma a1 is maximum, what you say is that with a probability epsilon, I will take an action which is completely random. So that random action can be A3, which will allow you to explore more actions which are not explored previously. And this policy is called as epsilon-greedy policy. What the epsilon-greedy policy allows you to do is that it allows you to explore the actions which have not been explored previously, and eventually update this queue function in such a way that all possible actions are explored. So for every state, you know which action is the best because all the actions are explored by the agent. So this is the epsilon greedy policy which we used for updating the action value functions for the Monte Carlo methods. So what our strategy was, we'll first calculate the action value function using the prediction methods. So I'm using the word action value function several times in case you don't remember it from the previous lectures. What it simply means is that if I am in a specific state and I take an action, then what is the expected reward for me in the future? So, whenever the policy is optimal, it will always choose actions which have the maximum value for the action value function. Okay, so the first step was to estimate this action value function, and then after that, we use epsilon greedy policy to choose actions for each state, and then we again update this action value function. So this process continues recursively. We have first one policy which we assume to be an initial policy, which is a random policy. Then we estimate the action value function for that policy by repeatedly going through the episodes. And then what we do is that we update that policy based on epsilon greedy actions, which means we look at the updated q values and we find which q value is maximum for each state and action. And depending on these updated q values, we decide our actions for each states. And then once in a while, we take actions which are random. So we follow an epsilon greedy policy. So this is also an iterative this is also policy iteration in a way, which is what we looked at in dynamic programming, but this is much more implicit. So you don't explicitly say that you are iterating the policy, but essentially you are, because uh, the queue functions, these queue values are being updated after every single episode, and your epsilon greedy policy is deciding actions based on this queue function, so they are also getting updated every single episode. So that is why these two processes are happening simultaneously. So in a nutshell, what we are doing is that we are using an epsilon greedy policy. We are updating the action value function by repeatedly performing the episodes multiple number of times. And what we see is that if you perform the episodes enough number of times, the action value functions converge to an optimal action value functions, and the policy also converge to an optimal policy. Now, in in the on policy, or in the control problem for the temporal difference methods, uh, we are going to use a very similar approach. Instead of predicting the value functions for a state, we want to predict the value function for a state action pair, which means that if I am in a state and I take a specific action, then what is the value of that action? In other words, what are the cumulative rewards which the agent will receive in the future after taking that action? And then this formula is exactly the same as the TD update we saw for value functions. The only difference is that the symbol V is replaced by the symbol Q. So this is the next reward, and this is the value function for this is the action value function for the next state and the next action. And this is where we come to the terminology Sarsa. The reason why this algorithm is named as Sarsa is because you look at all of these terms. This update uses ST, AT, RT plus 1, ST plus 1, and AT plus 1. So it is using SARSA. That is why the name Sarsa is being used. Uh, so it's really quite an intuitive algorithm. Once you have understood the prediction problem, the control problem really follows from that. The only difference we have to do is we have to replace the value functions with the action value function. And now to solve the control problem, we again use the method of policy iteration as we did for the dynamic programming and the Monte Carlo methods. Uh, okay, so now what we are going to do is that we are going to use a very similar approach as we did for Monte Carlo methods. And before we understand that approach, let us take a specific example. Let us say we are in state S and there are three possible actions A1, A2, and A3. And our policy tells us to choose action A2. Our current value function gives us the following values of the actions. We have the value function 32, 28, and 45. So clearly our policy is not optimal and we should choose A3 instead of A2 as suggested by our policy. So this would be a greedy policy, which means that for every state we are calculating the estimates of the action value functions and we are choosing the action which gives us the best estimate. So this is the greedy policy, but the problem with this is that our agent might not explore other policies. And for this same reason, and as we did for the Monte Carlo methods, we use an epsilon greedy policy to balance exploration and exploitation. And this is how the Sarsa algorithm is built. So essentially, the heart of this lies in this update, and the policy used is epsilon greedy policy. So what we do is that we initialize the states, and then there is action value function is initialized randomly first. Then for each state we choose an action from that state using the epsilon greedy policy. And then once an action is taken, let's say from this state, I take an action and I reach state S dash. In the meanwhile, I observe reward R dash, and from this state, I again take another action, which is causing me to go into a next state. So this action is A dash. Uh, Now, in Sarsa, what we do is we update the estimate for the action value function by using this the q of S dash comma A dash by using this estimate. What is the estimate for the action value function for the next state, and we add this reward along the way. So this is quite similar to the TD update that we looked at before, where we were just looking at the next state for the value function, but for the action value function we have to look at the next state and also the next action. So this is how the policy is implemented in practice. uh, we are going to states, we are choosing actions from that states, and then we are reaching some other states, we are again choosing an action from that state. Both these actions are chosen using the epsilon greedy policy. So the policy iteration is happening over here, but it is quite implicit as we discussed in this lecture itself, but I was discussing that for Monte Carlo methods. So you can do a one-on-one comparison of this algorithm versus the dynamic programming algorithm, and you will see, you might wonder, where is the policy iteration, is it missing? But that's actually happening because this epsilon greedy policy is looking at these action values and choosing the maximum ones most of the times, and these values are in turn changing every single episode, which means that your policy is changing every single episode. Okay, so this is the This is the Sarsa algorithm, which is used for TD control problems. And you might have noticed I have used the word online here in the this is on policy TD control. Now we are going to understand the true meaning of on policy and off policy methods in this lecture. You will encounter these words several times, even if you research about reinforcement learning methods applied to large language models. You will see on policy, off policy used several times. So, we are going to understand this at a basic level now. And that brings us to the next algorithm, next TD controller algorithm, which is called as Q learning. Now, this is an off policy algorithm as compared to the previous Sarsa algorithm, which was on policy. Okay, so let's understand off policy learning and we'll take an example for this. Let's say first we will look at just on policy learning and then we'll understand off policy learning. So let's say we are trying to ride a bicycle and okay, so the way you are riding your bicycle now is your current policy, and you are trying to get better at your style of riding. You are making mistakes, but you are learning from your own mistakes and you are changing your policy. You take notes about what happens when you follow your current style, and uh, you are updating your riding style based on your own learnings. So you're learning how to ride based on your own learnings, and this is exactly what is on policy learning. You are learning the same policy which you are following. So you are riding a bicycle and you are following some policy for that, but you are learning the same policy because you are learning from your own mistakes. You are taking notes about what happens when you follow your current style. This is called as on policy algorithms, where there is a behavior policy and there is a target policy, and both of them are the same. So in the Sarsa algorithm, the behavior policy was epsilon-greedy policy, but the target policy was also the epsilon-greedy policy. So the agent was learning a policy and it was actually following the same policy. But now let's look at off policy learning. Imagine you are still riding a bike, but you are watching a video of a professional cyclist. So you still ride around, you try things, you make mistakes. But when you update your understanding, you ask the question, what would have happened if I had balanced the cycle perfectly like the expert? So, what you are doing is that you are following the expert and you are updating your current policy based on your learnings from the expert. So the policy which you are learning is that of the expert, but the policy which you are following is your current policy. So you are behaving one way, but you are learning about the other way, which is the better way. This is called as off policy learning. And we do this quite a lot whenever we are learning something. If you have access to some expert, you try to imitate them. So you are following your own style, but you whenever you make some change, you try to see, okay, how are they doing it? Okay, let me try doing something similar to that, etc. So this is the difference between on policy and off policy learning. In on policy learning, I learn from what I do, and in off policy learning, I learn from what's best. And Q learning is an example of an off policy TD control algorithm. It is one of the most important breakthroughs in RL literature. And this is because the algorithm is quite simple and it's quite effective as well. So it is given by a very small change from Sarsa. And before we understand that change, we will see what is off policy in the Q learning. So in Q learning, the behavior policy is epsilon greedy, which means that the agent is still going to select actions using epsilon greedy policy, but the target policy, which is the agent trying to learn from an expert, is a greedy policy, which means that all the time it's going to choose actions which are giving the maximum estimate in the action value function. And this is exactly why there is a small change from Sarsa here, where you see that there is a maximum coming over here. In Sarsa, we did not have maximum. We were just choosing the whichever action which the agent was following, because the target policy was same as the behavior policy. But in Q learning, instead of that, what we are saying is that whenever I am looking at my next state and action, I don't care about all the other states and actions. I will choose an action which will give me the maximum Q value. And uh, because I am always choosing the action which gives me the maximum Q value, this is a greedy policy. So the agent is behaving like an epsilon greedy policy, but for making the update, the target is using a greedy policy. So here, the expert is the greedy policy here, but the person who is trying to learn, the agent who is trying to learn, is still following the epsilon greedy policy. That is the intuition behind Q learning, and it proved out to be extremely effective. It's used quite a lot, and it has proven to be very popular. So we will now look at one practical example to understand the difference between Sarsa and Q learning. And this will, I think, bring out the difference in a very nice way. And you will get confidence to implement these algorithms in practice as well. So we are going to take an example of cliff walking. So you start at a specific point in this grid, which is denoted by S, and your aim is to go to this cell marked as G, which is the goal, and your aim is to go in the least possible time. That's why the reward is -1 for all the transitions. But if you go into the cliff, you directly go back to the start state, and your goal is and your reward is -100. So the agent has to learn to go from start to the goal by avoiding the cliff in the least possible time. Now, the actions for each state, you can either go left, right, up, and down, and the rewards are already given in the problem. So, I have given the Google Colab link in the description. I want all of you to run these codes for yourself and develop the confidence of implementing Sarsa and Q learning on such practical problems. So when you learn using Sarsa, you get a path which is like this, which is the safe path. This is the direct output from the code. Uh, I say it's a safe path because there is another path which is this, which is taking less time compared to the above path. But still, Sarsa chooses this path, whereas Q learning chooses the most optimal path. Now think about why this is happening. The main reason is that in Q learning update we have that maximum. We are choosing a maximum of Q of st plus 1 comma a, and because of this maximum, the agent always gives preference to paths which are more optimal rather than paths which are safe. So even if this path is optimal, many times the agent ends up going into the cliff. That's why Sarsa is much safer, where it optimizes that, okay, if I go in this path, of course the reward is higher, but my agent also goes into the cliff many times. So on average, maybe the reward is less, even though that's the optimal path. So I am going to choose a path which is much safer. And I think this mainly happens because in Q learning, our target policy is the one which is the greedy policy. So, because we have a greedy policy, which is the target policy, the agent also behaves in a way which always explores these greedy paths more. That is my intuition why the agent chooses this optimal path for Q learning. Now, as a homework, I want all of you to try to reduce the values of epsilon and see if both the methods converge to the true policy. What is epsilon? Epsilon is the parameter in the epsilon greedy policy. So the intuition is that if you reduce epsilon, both the methods would start to behave like greedy policies and they would converge to the optimal path. But that is an homework problem. All of you should decide and give me the comments in the comment section. So this brings me to the end of today's lecture. We discussed two very important control algorithms, Q learning, which is an off-policy control algorithm, and Sarsa, which is an on-policy control algorithm. The main difference is that in both the policies, the agent is in both the algorithms, the agent is following an epsilon greedy policy, but in Q learning, the target policy is a greedy policy. It's not an epsilon greedy policy, and that is incorporated into the update rule by taking a maximum. So the Q values are continuously updated after each step, not after each episode. After each step, the Q values have been updated. I might have said in the lecture that the Q values are updated after every episode, but that's not the case. They are updated after every step. And that is what we saw as the main difference between Monte Carlo and temporal difference methods in the last lecture. And as the Q values get updated, the policy also changes because the policy is choosing the maximum action value for each state. Uh, and this is how the agent updates its policy iteratively and converges to the optimum policy, as we saw uh, in this practical example of a cliff problem. Okay, so we have completed the trio of methods now, which is dynamic programming, Monte Carlo, and uh, temporal difference methods. I want to leave you with a question and a thought, which is in all of these methods, the value function for there is a state and there is a corresponding value for that value function. So this entire, so let's say for every state, there is a state S1, S2, and then there is a value function for this 100, 200, etc. So this is called as a tabular method, which means that the value functions can be described in the form of a table. Now, my question to you is that if we want to convert this tabular table into a form which is a function, so I get my states as an input and I give my action or my value function value as an output. Is it possible for me to develop functions like that? And what would the advantages be? Would it allow me to approximate values of states which I have never visited? Why haven't I considered that option yet? So, from tabular methods, can we move to methods which have functions? And then, what is a universal function approximator? So, this will actually help us dive into our next section after these tabular methods are completed. But I want to leave you with this question so that you come prepared for the next lectures. Thank you very much, everyone.